Hello, this is an exam paper walkthrough for Combined Science Chemistry Paper 1, 2018. Question 1. We've got a question about electrolysis, and it says investigates the mass of copper produced during electrolysis of copper chloride solution. So here's our electrolytes, and here is a carbon electrode and also another electrode which it doesn't say what it is. So which gas is produced at the positive electrode? So this one, our positive electrode. What gas is it? So we've got a choice. If it's a solution, we could have hydrogen gas, we could have oxygen gas, or we could have chlorine gas. And because the solution contains water as well. And so we need to decide if it's gone to the positive electrode, it's got to be either from chlorine is coming from Cl minus, or oxygen will be coming from OH minus. So which one is it? It's got to be chlorine, because when you have a competition between hydroxide and chloride, chlorine is produced. Next question. Copper is produced at the negative electrode. What does this tell you about the reactivity of copper? So we are comparing whether or not hydrogen ions or copper ions get discharged at the electrode. So we're comparing the reactivity of copper and hydrogen, and copper is less reactive than hydrogen. Here are some results of the experiment. So we've got mass of copper produced. So the copper coats the electrode, and it's asking you to interpret the results. So first of all, our mean mass produced after 3 minutes. So let's just check. The mean mass of copper produced after 3 minutes is going to be halfway between these two, but it will allow you some leeway, so 1.8 is what we need here. And the mass X of copper produced in experiment 2, so we've got a calculation that you can see on the mark scheme as well, but let's just make sure that we understand what we're doing. So experiment 2 is the bit that we need, and here's our mean value. So we're going to use all of these, the sum of all of these values divided by 3 to make 3.06. And our computed value is 3.15. The copper chloride solution used in the investigation contained 300 grams per decimetre cubed of solid copper chloride dissolved in 1 decimetre cubed of water. Okay, so let's have a look. 300 grams per decimetre cubed of solid copper chloride dissolved in 1. That's very strange wording, isn't it? It means 50 centimetre cubed of copper chloride solution, and we need the mass of solid copper chloride used in each experiment. So if it's got 300 grams per decimetre cubed, and we need 50 centimetre cubed, so 300 grams in 1000 centimetre cubed. So in 50 centimetre cubed, the mass is equal to 300 divided by 1000 times 50. 15 grams. Question 2. Sodium and chlorine given in the periodic table, but it's not giving you too much other information in the periodic table, but it's just giving you some kind of hint that this is a metal, and if you could say that it's in group 1, then it's going to lose electrons when it reacts. But more importantly, first of all, okay, 1 electron in the outer shell, and this is group 1, 2, 3, 4, 5, 6, 7. This is group 7. 7 electrons in the outer shell. Okay, and they are in the same period. Okay, so our difference is sodium has 1 electron, whereas in the outer shell, whereas chlorine has 7. And a similarity, they have the same number of shells. Because they're in the same period, they have the same number of shells. It would be even better to write the number of shells that they have. So let's just count from the very top. 1, 2, 3 shells. Okay. Next question, we've got to describe what happens when a sodium atom reacts with a chlorine atom. So I'm going to draw a diagram first, just to remind you what you've seen, but we are going to describe this in words. North, south, east and west only has 7. So we're going to say that this electron goes to this point. So the outer electron from each sodium, is transferred to chlorine. And I think I've got all the marks there just by describing it like that. So, but sodium loses 1 electron and chlorine gains 1 electron. But on other mark schemes we might need to talk about what is formed. To form sodium ion Na plus and a chloride ion Cl minus. Okay, and then it doesn't ask you to talk about the bonding, it's just there, so I will stop there. I've already gone beyond what the mark scheme needed, which was, I think, sufficient there, but just the 1 outer electron. So the reaction between sodium and chloride is an exothermic reaction. Complete the reaction profile. So let's just check. Yes, it's labelled axes, progress of reaction, relative energy. We've got a line for reactants and we need one for products. If it's exothermic, then the products have less energy than the reactants. So let's label this line products. And then a reaction profile has to have one of those humps in it, like this, and that's it. So it's not the same as an energy level diagram. So reaction profile means from the beginning to the end of the reaction, and that is that for 2 marks. So in the examiner report it says that people forget to label the line or things like that, but the main thing is that the line is below. Okay, now we have our first 6-mark question, so we are going to read the question really, really carefully and then decide how we're going to organise the answer. So a student plans a method to prepare pure crystals of copper sulfate. The student's method is add 1 spatula of calcium carbonate to dilute hydrochloric acid in a beaker. When the fizzing stops, heat the solution with a Bunsen burner until all the liquid is gone. Until all the liquid is gone. That doesn't seem right. So let's just remind ourselves of what we're supposed to do, the four steps that we need. So first of all, we're going to react. So we're going to add the solid to the acid. But we need to work out what the names of the solid are and the names of the acid in a moment. And then step 2 would be to filter excess solid, wouldn't it? Filter. And then we should end up with a solution of water plus the salt, and we'll give that the name that it says we've got to make is copper sulfate. Third step, we're going to evaporate the solution, I should say. Okay, and the fourth step will be cool, so that crystals can form. So we'll draw some crystals. Because crystals don't form, solid doesn't form until something cools down, so there you go, there's some lovely crystals there. So let's have a look and see. So add one spatula, that's not going to be enough, and also calcium carbonate isn't the right one. We've got to have copper carbonate. And it's no good just saying copper, you've got to say copper carbonate. Unless you give full names, you can't reach level 2. You can't reach level 3. And the acid that we need, well, we've got to make sulfate, so it's got to be sulfuric acid. Okay, and then we need to have excess copper carbonate. So that all the acid is reacted. So we've got to react the sulfuric acid completely. Then evaporation and crystallization, that's not in the method at all. Well, I suppose it is. Heat the solution until all the liquid is gone. But we have to be careful. Don't heat until dry. Only until crystals begin to form at the edge. That's for safety and also to get bigger crystals. Okay. So by drawing diagrams like this, you could get lots and lots of credit, but we do need to explain the improvements. So yes, we've got a new method, but we've got to explain why there's the improvements to make. So we could just write a brand new method, and when I was marking this, lots of people did that. But a better answer will say you have to do this instead because. So let's try and organise our answering using the numbering system that I've got here and just explaining what each improvement is step by step. So first of all, okay, change to copper carbonate and sulfuric acid. So the correct salt is made. Okay, I'm just going to change to the examiner's report here and just check. What does it say? Oh yeah. Question 3. Yeah. Improve a method. Explain. Some students could see that a new substance needed to be made, but they didn't actually explain. They didn't change things in the method, so they didn't get the marks because they didn't change the chemicals. They just carried on improving the method, and that limited people to level 2. So many students mentioned an improvement but failed to explain the reason for the change. For example, many students mentioned the need to filter but failed to state that filtering removed excess copper carbonate. So we're going to do that. And excess base was added but didn't justify to say that all of the acid was reacted. Okay, so let's do that. So change the copper carbonate sulfuric acid, so correct salt is made. Add copper carbonate until no more reacts. All the acid has completely reacted. Okay, and then in step 2 we're going to filter to remove excess copper carbonate. So the solution contains only water and copper sulfate. Okay, and it says that we've got to filter, so this is the extra steps now. So, but the evaporation is another extra step that didn't get mentioned. Well, it did, but it was really bad. So, evaporate until crystals by heating, only until crystals form. Until start to form. To what should we say, to avoid danger of the salt flying out of the evaporating dish. Okay, and to form bigger crystals, but I won't say that as well. I say finally, crystals will only form on cooling. So leave the solution, and you could say saturated solution, meaning no more dissolve, so it's going to start to crystallise. Use saturated solution in a cool place overnight. Okay, so let's just have a look at the mark scheme and see how that matches up. So indicative content is there for you, have a look. Question 4, a halogens question. So as always, group 1 and group 7 need revising really thoroughly, and they're going to test you on structure and bonding in this question. So state symbols, now this is a question that would be marked automatically or by a non-specialist marker, so there's no choice whatsoever. It's little g for gas, and that is it. That's the only acceptable answer, not capital G, nothing else. Dot and cross diagram, this is a really tricky one for examiners to mark effectively unless you pair up the electrons as much as possible. So I strongly recommend that you put your non-bonding electrons in pairs. So first of all, we're going to have a single shared pair of electrons, and then after that we're just going to have a total of 7 other electrons in pairs, please. North, south, east, done. North, south, east is done, and west is there. It just makes my life so much easier rather than having them like beads on a ring. So a fluorine atom can be presented as 19,9F. So let's just check the names of these. So this is the atomic number, but you call it proton number in physics. And this is the mass number. And the atomic number gives you the number of protons, which in a neutral molecule, there should be the number of protons equals the number of electrons. But we can also check it from above here as well. So we've got 2, 4, 6, 8, 10, 12, 14. Is that enough? No, because that's only the outer shells. So we should do 9 plus 9. Okay, 18. Aluminium reacts with bromine to produce aluminium bromide. Complete the balanced chemical equation for this reaction. So aluminium's in group 3, bromine's in group 7. So it forms Br minus and Al3 plus. So now we can combine those together to form a neutral compound with 3 plus 3, hang on, 3 plus 3 minus equals 0. So you've got Al Br subscript 3. So this is what's formed. So how do you get that to balance? There's 2 Als on this side and 6 Brs on this side, so we're going to use 2 times 3 equals 6 to help us. There you go. Okay, question 4.5. When chlorine reacts with potassium bromide, chlorine displaces bromine. So this is one of those set memorised explanations, and some students only just sort of repeated it or said that it's because of the periodic table. But that would get you a rescue mark, but not 3 marks. So we are going to go for the number of shells explanation. So if you look at the periodic table, we can see that chlorine has 3 shells and bromine has 4 shells. But they've both got 7 electrons in the outer shell, so they gain 1 electron when they react. Okay, so let's use that. So we're going to talk about how easy it is to gain an electron. So chlorine gains an electron more easily than bromine. There are fewer shells in chlorine. So the nucleus attracts electrons in the outer shell. So you've got to say outer shell more easily. So the way that it's phrased it in the mark scheme is quite useful. Let's use that, and I'll put it here, including an incoming electron. There you go, incoming. There you go. And I've worded this wrongly, more strongly. So the nucleus attracts electrons in the outer shell more strongly, including an incoming electron. Okay, question 5. More structure and bonding. So this is part of a giant structure. Okay, it's not a little molecule, and if we just analyse something that's in the centre of the structure, like this one here, you can count all the way around it and just see what is going on with this bonding. So let's count. We've got 1, 2, 3, 4. So each C is bonded to 4 C's. Okay, and it's got sticks, but that doesn't always help us. But it's a good sign that it's covalent, so we know it's giant. Okay, so we're just going to go structure and bonding. And we've got to explain the melting point. That's all we need to do. We don't need to talk about its hardness, its conductivity, anything else. So for 3 marks, we're going to say the structure, we're going to say the bonding, and then we're going to say why that melting point is high. So carbon in diamond has a giant structure with many strong covalent bonds. Each carbon is bonded to 4 others. The covalent bonds require a lot of energy to overcome. So I didn't repeat the question. I did use the word energy, not heat or anything else. Okay, so I've written a little bit more than is required by this mark scheme, but I know that sometimes mark schemes vary, so I'm going to go for that bonded to 4 other carbons there as well. Okay, question 5.2. Figure 6 shows part of the structure and bonding in sodium chloride. So sodium chloride, we've got a metal and a non-metal. We're expecting ionic bonding, and it's got ions. Great. Okay, so the conditions needed for sodium chloride to conduct electricity. I am going to state the structure and the bonding just in case. So sodium chloride is a giant structure with ionic bonds. In the solid, ions cannot move. If the ionic bonds are broken by melting or dissolving in water, to form an aqueous solution, that is. The ions can move and so charge can flow through the substance. So I've written a lot more than the mark scheme said, but again, it's insurance against more modern mark schemes which are more demanding, or for other styles of question. So let's just check what it says in the... Yeah, okay. So in the examiner report it said generally students missed out on full marks because they only included one way to produce ions, either dissolving or melting. And sometimes people said molten or liquid, but that's not right. You've got to say molten or dissolved in water. And it's a common mistake to talk about electrons. It's just ions in this situation. Okay, and 3 in a bunch. This is a horrible thing to mark, so keep your points separate and don't repeat the question, and don't contradict yourself by writing too much, because the examiner will be quite bored by now. So 5.3, describe. So you've got to describe with like this diagram. We've got sodium here, so we've got positive metal ions fixed in place, and not shown in the diagram is the delocalized electrons. Okay, so how does it conduct thermal energy? So you've done much more practice on conducting electric current. So we've got to make sure that we understand that it's not, when thermal energy, yes, vibrations are passed on, but also that's an energy transfer by things bumping into each other. But here we've got the delocalized electrons actually moving, and they're transferring thermal energy through the material. So again, we've got some kind of direction to the movement, say. So this is hot, let's say, and that's cold. So describe how sodium conducts thermal energy. So delocalized electrons move through the material. I'll say metal. So thermal energy is transferred. That's it. Okay, question 6. We've got group 2 metal carbonates thermally decomposing to produce a metal oxide and a gas. So this is not on your specification. It's just asking you to apply your understanding to an unfamiliar reaction. Give the formula of each product when calcium carbonate is heated. So it's got a metal oxide. Let's just rub out that exclamation mark, it's in the way. And a gas. Okay, carbonate. Ooh, that does remind me of when these things react with an acid. I think the clue's in the name. Okay, and a metal oxide. So let's find out what the metal's name is. Calcium. So we've got calcium oxide, and the clue's in the name, carbon dioxide. Okay, 6.2, the relative formula mass of a group 2 metal carbonate is 197, and it's giving you some relative atomic masses. Calculate the relative atomic mass of the group 2 metal in the metal carbonate. So this is a different question part. It's not calcium again necessarily. Let's find out which it is. So we've got to write a little sum. So the relative formula mass, Mr, equals sum of AR, okay, equals, so let's say let AR of metal equal X. Okay, and so we can say that if it's a metal carbonate, it's in group 2, there's going to be one metal plus one carbon plus 3 times 16 for 3 oxygen atoms. If it's in group 2, it's going to have the same kind of formula as this. Calcium carbonate equals 197. So we can calculate that we have 137. X equals 137. And it's barium. So figure 8 shows the volume of gas produced when a different group 2 carbonate W is heated. Okay, so it's a different one. It's not barium carbonate, it's not calcium carbonate necessarily. And it's asking us for the gradient of the line. So we're going to do a massive triangle. Okay, so I want to make this as accurate as possible. This is going to be slightly difficult on screen, but I will try. That's not a line. Let's try that one again. Okay. So this is actually time consuming and awkward for me, so I think if you just make sure you draw a big triangle, then we'll do a lot better. Let's get rid of that. So draw a big triangle. A big triangle to reduce your error. Okay, and you should be able to do this and come out with something which is a nice big line. Okay, another one. Good. Okay, so ultimately when you've got your difference in y's and difference in x's, you should be able to get something along the lines of 335. So difference in x, difference in y, sorry, over difference in x equals 335 over 2.0. Take away 0 for both of those. That's about 168, something like that. Okay, and then we've got some units to give as well. And so the units should match up to the units for above and below. So this should be centimetre cubed and this should be grams, and I divided one by the other, so it's centimetre cubed per gram. Okay, 24 decimetre cubed of gas is produced when 1 mole of group 2 carbonate is heated. What's the relative formula mass of group 2? Whoa, okay, so how do we work out that? Let's have a look. So the volume of gas and the mass of group 2 carbonate, and then we could probably work out the relative formula mass from, yeah, okay, so we're going to need to end up using mass yeah, so mass equals moles times mR is the way I've learnt it, so now I need to rearrange that. mR equals mass over moles. Okay, so that's in the right order. So we've got some mass, and then we've got this gas thing. Oh, so from the graph, find the mass. But the graph doesn't go up to 24 decimetre cubed. Does it go up to... what's the closest it goes up to? Oh, maybe 240? 240 centimetre cubed. Okay, let's use that. So if 240 centimetre cubed comes from something on the graph, let's see, from the graph, let's work out how many grams that comes for. And this is also, we know that that's 24,000 centimetre cubed. Then I reckon we could say then 24 decimetre cubed of gas is produced from that many grams times 10. So let's work that out. So 24, 240, where's that? There. Okay, so let's draw a decent line. Accurate to within half a small square. Not that line, this line, new line. Oh, it's not going to be easy for me, sorry. I'll do it on here. Okay, so I think that reads 1.1, 1.2, 1.3, 1.35 maybe. It's saying 1.45 here, so I'm just going to go with that. 1.45 grams from the mark scheme because my line is just a bit rubbish. So that comes from 1.45 grams. So that will be 14.5 grams. So does that make sense? No! We've got to times it by 100, not by 10. So 145 grams. Okay, and so that means that the mass of 1 mole, so 1 mole has a mass of 145 grams, or you could say MR equals 145 times 1 equals 145 grams per mole. 145. Okay. As you can see from the mark scheme, there was an alternative for that, which is just not using the graph, but using your answer from question 6.3. Okay, question 7. So this is another one where we have investigation of an unknown practical, or unfamiliar practical, let's put it that way. And what we need to do is to look at all the evidence, and then we're going to organise our answer to create an unstructured question. We're going to make a really good structure for our question, identifying the solids A, B, C and D with explanations. Okay, so how many different bits of evidence have we got? We've got test 1, test 2, and we've got the identities of the 4, but we don't know which one is which. Okay, and then what else does it say? Oh yeah, the solubility in grams. So we're trying to match this to this, whether or not any solid remains. And if something doesn't dissolve at all, it can't have a pH either. Okay, so it wouldn't actually just, you wouldn't be able to measure the pH of the thing, so you would just be getting the pH of water. If it doesn't dissolve at all. So if there's solid remaining, that means low solubility. So there will be solid left, and solid will be left. Whereas this one, we're expecting no solid at all. No solid left. It all dissolves. No solid. Okay. What else? This pH thing. How would we know whether something was became an alkali? Oh wait. Some of these look like bases to me because they're metal oxides. So metal oxides are bases. Okay, and soluble metal oxides are alkali. Alkaline. Okay, so let's have a look. This is a metal oxide, this is a non-metal oxide, this is a non-metal, this is a metal. So solid was left, so that's a base but not an alkali. Okay, and this one, if there's no solid, it dissolved, that is a base and an alkali. I think we have enough information now to work it all out. So we're going to say that this one is a base, this one is an alkali plus base, and this one no pH. So this one is like some other pH. Oh wait, yeah. So we could say query the low pH one. As it happens, a non-metal oxide is usually acidic, like sulfur dioxide, SO2, because that forms acid rain, doesn't it? So that's a comparison that you could make. You don't have to at all. Okay, so let's have a look and see what we need to say. We might not need to say loads, so let's just have a look at the mark scheme. So you've got to identify them all. Let's have a look. Relevant points are identified, and then for level 3 you've got to say detail and logical linking to form a clear account, whereas if you only try to link it logically or it's not fully clear, then we have got only level 2. So my advice would be that we need to identify them and explain them. Okay, so treat each separately. Okay, so there might be a bit of moving the paper up and down here so that we can just get this sorted. So if we've got, let's have a look. A is colourless, no solid, and it's pH 14. So we are expecting it to be alkaline, and that must mean it's sodium oxide. So sodium oxide is A, is sodium oxide, because it dissolved completely. To form an alkaline solution. Demonstrating it is a soluble base / alkali. Okay, B. Colourless solution, no solid, so it fully dissolved and it's an acid. So we're expecting it to be phosphorus oxide because it did dissolve, but it's not a base. Give the full name of each chemical to get into level 3. Because it is soluble, it dissolved, but formed an acidic solution. C. It's a colourless solution but some solid remains. It didn't dissolve properly. So it could be magnesium oxide or silicon dioxide. Oh wait, it says solution. Some of it did dissolve. and then the pH did change, so this is the same as water, and it was just a liquid, it wasn't a solution. So we can tell the difference clearly between C and D. C dissolved only slightly. And was slightly, the solution was slightly alkaline. So C is magnesium oxide. D was completely insoluble, so no solution was formed. And the pH was unchanged from water. At pH 7. So D is silicon dioxide. It's sand. Okay, good. 7.2, 10 centimetre cubed of solution B. What was that again? Oh, wait, the acidic one, phosphorus oxide. Okay, so distilled water is added to the beaker until the final volume is 1,000 centimetre cubed. So knowing that I got this wrong in the previous question until I corrected myself, we've got it's more dilute by times 100. The pH of the solution is measured before and after distilled water is added. So times 100, every time you take the volume and you dilute it by 10 times, you change the factor by 2. So this would be, it's got to either increase or decrease by 2. So if we've got it more diluted, then it's less acidic now after dilution. So it goes up by 2. So to show that you're calculating it somehow, you can write this or calculate it like this. 1,000, okay, it's 100. Factor of 10 squared. pH increases by 2. X equals 5. Okay, question 8. Again, there's going to be some unfamiliar stuff in here and some calculations. But we do know that we have to know all of those metal plus acid reactions. Metal plus acid makes salt plus hydrogen. MASH. Name the other product apart from iron chloride, hydrogen. How could any unreacted iron be separated from the mixture? So all the separating techniques we know, let's just write them down. So we've got filtration, we've got evaporation and crystallization, we've got distillation, and we've got chromatography. Those are the 4 separating techniques we've got. Now iron's a solid and it's insoluble. So this is the one, filtration. Don't write too much. One word's enough. And a magnet would work as well, hooray. Okay, so magnesium reacts with iron chloride solution. 3 magnesiums and 2 iron chlorides. That's that one. Okay, 0.120 grams of magnesium reacts with excess iron chloride. Calculate the mass of iron produced in milligrams. Okay, so 1,000 milligrams in a gram. Okay, so it says that many grams of magnesium and there's lots and lots of iron chloride, and we're just interested in how much iron is produced. So we can see we can use this ratio. 3 mg's make 2 FEs. Okay, right, and that's all we actually need. So I'm going to do word method and table method. So 8 mg plus 2 FeCl3, 2 Fe plus 3 mgCl2, and I'm only interested in this bit and this bit, and I'm going to use my ratio once, not more than that. Okay, so I've got a mass and I've got an AR. I'll call it AR because they're both, it's given in the question as AR, isn't it? And then I'll do moles down the side. So our mass is 0.120 grams. I'll do the conversion right at the end, I think. And the AR of magnesium is 24 and of iron is 56. Okay, so I can get my moles straight away. So that calculation being moles equals mass over relative mass, 0.12 over 24, so I've got 0.005 moles. So 3 moles makes 2 moles, so that's like times by 2 on 3, so 0.005, let's put my calculation over here, times 2 on 3 equals, oh, it's not a very nice number, 0.00333, so plenty of significant figures, and then to get to there I need to times, to get mass equals moles times AR, so 56 times 0.00333, so that's in grams, we've got 0.1866, and then I can times it by 1,000 in milligrams equals 0.1866 times 1,000 equals 187, rounded up to 3 significant figures, because that's that's what the mass we're given here. It's got 3 significant figures, so I'll use 3 significant figures. Okay, so 187 milligrams there. Now let's just use our word method as well. So we're going to do moles ratio, moles, and then our something else that we have to do at the end this time is mass in milligrams. Okay, so moles of magnesium equals 0.120 times, divided by 24 moles of Mg to Fe is 3 to 2, so moles of Fe equals 2 on 3 times 0.005, so mass of Fe 56 times 0.00333 in grams, and mass in milligrams. equals 187. Okay. Question 8.4, our last one. Explain which species is reduced in the reaction between magnesium and iron chloride. So oxidation and reduction. Oxidation is loss, reduction is gain. And we're talking about electrons. So let's have a look. So this is an element. So, and then it turns into a compound. So this is oxidized because it turned into a metal ion, and so chlorine, no change, because it's still in a compound, and iron itself has been reduced because it went back to being an element from a metal ion. So metal ions is loss of electrons to form positive ions, right? Okay, so iron was, hang on a minute, yeah, iron was reduced. Okay, it gained electrons. Okay, now we need to have a workout of how many. So FeCl3, we know that chlorine's in group 7. So it has 7 electrons in the outer shell, and it gains 1 electron when it reacts. So we've got chloride iron is Cl minus, and there are 3 of them. So a neutral compound, if this one's minus 1, so we have 3 times minus 1, and some other charge here equals 0. The other charge here is plus 3. So charge on Fe ion is plus 3. So that's how we're starting from the iron, and I'll write it as 3 plus, and you end up with reduction is gain of electrons, so you end up with iron, which is neutral, so we have to have some minuses on this side. Electrons are gained, 3 of them are gained. I'll just put the mark scheme up. Okay. Alright, thank you very much everybody. Look out for paper 2.